right. Welcome, everyone. It's a new month, and we've chosen a meaty subject to boost everyone's curiosity and learning. So, bleeding edge technology is our theme, unlocking the future of human innovation. This is going to be a 4-part webinar series, and it will delve into the most exciting and transformative technologies of our time. Our experts will speak and guide you through the latest advancements in quantum computing, artificial intelligence, neuromorphic engineering, and the integration of these technologies into your organization. So we hope you'll join us every Wednesday in August for this series. And today we are going to start with quantum AI fusion, as you see here with Scott. Let's get started. We're diving into a frontier where two of the most groundbreaking technologies, quantum computing and artificial intelligence, are converging. This session is your gateway to understanding how quantum hardware works and why it matters. We'll explore how hybrid quantum classical algorithms are not just theoretical. They're already unlocking breakthroughs in optimization, modeling, and real-world applications like drug design and logistics. So whether you're curious, skeptical, or already deep in the weeds, you'll be in the right place for the next leap in computing. And before we begin, let's a little bit of information about our speaker today. Welcome Scott Poulin, who's Vice President of Technology and Improving. With a strong foundation in physics, business, and information systems, Scott brings deep expertise in back-end engineering across industries like transportation, finance, healthcare, and nonprofits. His passion for machine learning, AI, and quantum technologies drives his mission to deliver meaningful innovation and positive change through software. So, Scott, before I turn it over to you, I'd like to invite our audience to participate by using the chat to add questions as we go along. And I know you've got a lot of information as we discussed before the talk, so I'll hand it over to you.
Perfect. Thank you, Lynn. Appreciate it. Thank you, everyone, for joining today. Hopefully, this will be a pretty informative talk for you. My goal here is honestly just making sure that I provide as much information as possible. Lynn already gave a perfect background of who I am and what I do. One of the big things about me and why you should probably listen on this is I've been in the AI space now for about 15-ish years. And then on top of that, my background, I have my physics degree, as previously said, and I specialized in quantum theory and quantum computing. So that's kind of my realm and why I love this aspect of it. And so trying to meld the two joys in my life of AI and quantum computing together, and hopefully be able to see some of that here today on this talk. So we'll jump right into it. So for our agenda over the next about 50 minutes, it will be as follows. First, a brief overview of quantum computing fundamentals, key concepts like qubits, superposition, entanglement, and why quantum computers work differently than classical ones. Next, we'll discuss why quantum computing matters, what advantages it offers, and where it can add value. Then we'll delve into quantum AI, explaining how quantum computing intersects with artificial intelligence. I'll spotlight an example, quantum natural language processing, or QNLP, which encodes language meaning into quantum states. After that, we'll survey the current quantum computing landscape, the cutting edge hardware, the cloud platforms, and software development kits, a bunch of other things, and things that you can use today to start looking into your quantum computing realm. We'll then explore industry-specific applications in 4 different sectors: finance, logistics, energy, and pharmaceuticals, to see concrete examples of how quantum computing prototypes and their operational benefits in each domain. Following the use cases, I'll candidly address the challenges and realistic expectations. What's the state of the technology? What are the limitations like noise and error rates? And then likely timeline of for the progress of what to look forward into the future. Finally, we'll look at a roadmap of how to become part of the quantum readiness practice, or just practical steps for leaders and engineers to prepare their organization for the quantum era. We'll wrap up with the conclusion and then prepare for any questions that for folks that may have that go through this presentation today. So throughout this talk, my goal is to hopefully, if you're a quantum expert, I hope that you'll get a broader view of how quantum computing affects the broader business implications that are out there. And if you're a business leader, and to kind of demystify, per se, the tech without oversimplifying it. So with that being said, let's dive in. So for first and foremost, I mostly just wanted to go through some key terms that are kind of important to understand. Just from the quantum computing perspective, qubit is effectively, you can think of it as a normal bit, but with quantum computing, it has a state of 0, 1 when it is at its rest state, but when it can be in its what is called superposition. Effectively, when it's in that state, it could be either 1 or 0, or anything in between, even into the imaginary realm, if you're familiar with mathematics and imaginary numbers. So I know that sounds kind of weird and kind of mystical, but it's effectively just a representation of a bit, but in a quantum computer. Superposition is effectively the state in which it goes into what we commonly refer to as like the quantum state. It allows it to be in that realm of 0, 1, or at any given point in time. And without it being measured, we won't know if it's a 0 or 1. And so that's where this realm of measurement comes into play. And with that aspect, it's observing the qubit and seeing what state it is in, and it effectively falls into 0 or 1. And then entanglement is just this aspect of qubits kind of being correlated to each other and understanding as to what they are and how they affect each other and implement across. A block sphere is just a 3D representation of what a qubit looks like, because typically individuals only see it as the binary aspects, and so it's only 2 axis up and down, or it's just a single axis aspect, but there's multiple states to it, and so there's a bunch of different representations that you can look at it in a 3D representation. Quantum gate is just it's very similar to logic gates within inside of computers. It just has to do with like various different types of logical implementations. And then a quantum circuit is just a combination of those gates to perform some sort of functional activity on top of that. No cloning theorem, real quick on this. This is just a theorem that's within inside of quantum computing, in the sense that you can't copy quantum states, unknown quantum states from at all. So you just can't make a replica of it. And then decoherence, this is just essentially the aspect of noise impacting your environment of your qubits. So most of systems have a very kind of sensitive environment that they live in, and any sense of effectively what they call decoherence or impacts to their environment can result in errors, which you see there is error rate. And then over fidelity is just, error rate is like the failure of it to be predicting wrong, and then fidelity is the correctness of the qubit itself when predicting in a logical format. So, and then quantum error correction is just the sense of using other qubits to effectively make one logical qubit. And I'll get to logical qubit here in a second, but effectively it's just a methodology that allows you to use other qubits to correct one other qubit to have a functional rate. So there's effectively a process that you use qubits to help reduce the error in another qubit to make sure that it is actually logically calculating the thing that you're looking for. And then the logical qubit is effectively this combination of qubits that help make sure that the error or decoherence is reduced with inside of a single qubit. And then NISQ is just effectively talking about our kind of modern day technology that we have that for sensor readings and a bunch of other things like that results into low fidelity in the sense of like properly reading something. A lot of our devices that we have today don't operate well in the sense that they don't provide high accuracy reads on qubits, and so that results in more error. So a lot of different things there, but just things I want to call out because they are talked about pretty widely with inside of this talk today. So that being said, let's get started with the basics of what is quantum computing. In simple terms, it's a new computing paradigm that uses quantum bits or qubits, as you previously mentioned, which follows the laws of quantum mechanics to process information in fundamentally new ways. A classical computer bit can only be 0 or 1 at any given point in time. A qubit, in contrast, can exist in a superposition of 0 or 1, essentially being 0 and 1 at the same time. At least that's what it looks like, or until you measure it. The superposition means a collection of qubits can represent many kind of combinations of values simultaneously. For example, 2 classical bits can hold 1 or 4 possibility states, 0, 0, 0, 1, 1, 0, 1, 1, but the qubits can exist in a combination of all 4 of those at any given point in time. So if you have many qubits, the amount of information you can represent exponentially grows. So now that we can have all of that. So entanglement is just another key principle inside of that. As previously mentioned, this is just a quantum phenomenon where qubits become correlated in such a way where their state of one qubit is instantaneously influences the state of another, no matter how far apart they are. So this is kind of one of those big things that's really important inside of quantum networking and a bunch of other stuff, which we'll get to later. And then additionally to that, another important aspect is, as also previously mentioned, is measurement. It's just the aspect of you observing the quantum of their qubit state. This forces what we call the qubit to effectively collapse and fall out of its quantum superposition. And so it comes down to a value of 0, 1. And so based off of that, and if you have a high fidelity system, you have a high probability of predicting whether it falls into 0 or 1, which allows you to do a lot more accurate measurements of how to make various different types of calculations. And so it's a lot of what this is just this choreographed movement of like understanding the various different aspects of the qubits and how they fall and a bunch of other things as they fall out of superposition, all that. So to sum all that with superposition, entanglement, and measurement, all of that, that kind of leads us into kind of a bunch of different examples where this kind of effectively helps us understand as to how to use this in quantum and a computing sense. So using other like quantum algorithms, one that has come out of it is Grover's search, which is effectively a search over an unstructured database that can actually find things inside of that database quadratically faster than a classical method. So, and then Shor's factoring algorithm can factor large numbers exponentially faster than best known classical techniques. And so this is not necessarily just theoretical. It's a true proven principle in which how quantum computers have the capabilities to go beyond classical limits in certain domains. Big keyword there, certain domains. So it allows me to, I guess, let me emphasize in the sense of like taking away up front, quantum computers will not replace like classical computers for everything. For example, you won't necessarily just get rid of your laptop one day because you have a quantum laptop. That won't be a thing. Your laptop will most likely remain with you forever, and you'll just have a newer laptop that does classical computing. Most of these quantum machines are more likely specialized for coprocessors or accelerators for very hard problems in optimization, simulation, cryptography, and a bunch of other places. So like it's just not going to be something that you have to have inside of your home one day. So that being said, having sung the praises of qubits and have addressed some practical reality and challenges of today's quantum hardware, qubits are something to be understood as they're very extremely fragile. They can maintain the superposition and entangled states only for brief moments because of interactions with the environment, as I kind of mentioned, and the aspects of where decoherence kind of comes into play. This essentially means that even the most high fidelity systems that can handle a bunch of different error probabilities, we're still in the orders of magnitude of 0.1% to 1% per operation when it comes to error probabilities. Now, from a single perspective, that may not seem like a whole lot, but I mean, we're also seeing this in agentic AI as well, where if we have 0.1% to 1% error, but that compacted over hundreds of events results into a high rate of probability of error at the end of your sequence. And in computing, we're not looking at hundreds, we're looking at thousands to hundreds of thousands or even millions of operations that occur. So at even 0.1% error rate compounds over 1 million operations, you're getting a very high error rate at the end of that. So that's where kind of a lot of this is kind of showing difficulty. But there's a bunch of different techniques that we can get around that to kind of help with that. Most of what is being done now is that most quantum computations are fairly short and shallow circuits. So effectively, they're just very short circuits to make sure that we can have a high level of confidence in that whatever we calculated was accurate. Bottom line is that we're in the era of quantum computing, very, very start of it. But it's very similar to like what happened in the 1940s and 1950s, where a lot of classical machines are being built and doing calculations. They're fragile, expensive, and limited. But we're kind of starting to enter that same era for quantum computing. And so there's a sense of hopping on and starting to gain some quantum advantage where quantum computers can technically perform meaningful calculations significantly faster than classical ones. So it's not yet in a really broad commercial sense that it'll be helpful, but the estimates will show that it's on the rise and it's coming. So that being said, so why should you care now? If it's not really ready for the challenge to change the world, the honest reason is because the potential is so enormous. Quantum computing matters not as a replacement for classical, but as a powerful complement that can handle certain problems that stump classical computers just due to the complexity or the high level of computational need for it. So we can explore a bunch of different vast solutions in this parallel space. For instance, evaluating many possible configurations of a system at once with different dramatically speed up tasks like finding optimal combinations or simulating complex systems. So the big thing here is that anything that is computationally heavy for classical computers as they grow in size and complexity is kind of just one of those key areas as to where quantum computing can come and effectively help. So that being said, I'd like to start looking at past the whole foundations of concepts and current limitations and start looking at the aspects of quantum computing and artificial intelligence. Just because there are certain limitations to it, it doesn't necessarily mean that quantum computing is not necessarily going to be something that happens today. There's a lot of different techniques in how we can effectively deal with quantum computing's potential errors and issues. A lot of that comes into play where we can actually introduce AI and machine learning to help with quantum computing on its side of things. So going into that, most of like what we're going to look at today is looking at how quantum AI is actually something that we're going to look at, just because it's kind of used today to help. The latter aspect is commonly used today to help us understand how to make quantum computers better and more effective. But the real fun question, I think, in my sense, is that how can we use quantum computing to take AI to the next level? One of the big things here is that they're really looking at potentially using it for faster training of models, new algorithms for machine learning, and kind of diving into that realm. So we'll start talking about a little bit that today. So the promise of quantum machine learning is that certain linear algebra tasks at the heart of AI, such as solving large systems of equations, matrix operations, sampling from probability distributions, etc., might be done more efficiently on a quantum processor. For example, there are quantum algorithms for solving linear systems that theoretically offer exponential speedup over classical methods, and quantum amplitude and amplification that can accelerate sampling or searching tasks. If these are harnessed with machine learning workflows, we could potentially train models faster and handle larger data sets than classical machines allow today. So, however, it's important to note that quantum machine learning is still relatively largely researched and experimental. So that's just something to kind of take home with you. But That being said, there is kind of a newer realm that's popping up. This was something that I learned about only probably about 6 months ago, was that it's called quantum natural language processing, or QNLP, basically applying quantum computing to understanding and processing human language. One approach to QNLP is pioneered by Cambridge Quantum, which is now technically called Quantinium, is to encode word meanings and grammatical structure into quantum states. This might sound kind of abstract, so I'll break it down a little bit. In language processing, one challenge is capturing the nuances and context of words and sentences. Words can have multiple meanings, and meanings can be correlated together. Think like analogies or context-specific interpretations, grammar rules, connected words in complex ways, a bunch of different things. The QNLP approach uses mathematics of quantum states to represent these linguistic elements. Here's like kind of a conceptual picture that you can think of. You represent words or phrases as qubits, qubit states, or collections of qubits. Because qubits can exist in superposition, a quantum representation of a word and principle encoded multiple meanings or interpretations all at once. So this is kind of like a way to use, like, for there is in a sense, it's spelt different, but it's also heard the same, and there's different ways to use it. And so that's a very similar aspect for that. And so you can actually imply entanglement to kind of play another role to help structure the sentences, combining words according to grammatical rules, and can be seen as entangling their quantum state representations via operation. So there's a bunch of different little things inside of there. But why bother doing this on a quantum computer? Proponents argue that there are several advantages. First is native superposition. A quantum computer can naturally hold a combination of meanings, interpretations, and process them simultaneously, potentially leading to a richer context disambiguation. Effectively, the computer might more easily handle ambiguous language where a word or phrase could mean multiple things. Second, potential speed-ups in linear algebra tasks like comparing the similarity of meanings or retrieving relevant information from a large text might be accelerated by quantum subroutines. This has to go back to that Grover search functionality aspect that I mentioned earlier. And then third, high-dimensional representations. Language has combinatorial complexity, the number of possible sentences or meanings in an astronomically large kind of sense. The quantum state can be represented extremely high dimensional vectors implicitly, which could allow for more nuanced semantic search across huge corpora of text. In short, QNLP could offer a new way to encode and manipulate language that might yield more powerful language models in the future. So that's a benefit for us. With that, now that's just kind of a dream. Where are we today? Today, QNLP is highly experimental. The hardware is the major limiting factor. Quantinium has actually put a pretty awesome roadmap to kind of show this, but they're constantly going out and doing a lot more research around this, and the big thing in the aspects of noise and scaling are their biggest challenges. But with the hybrid path that they're trying to follow, they can actually start to look at using like quantum kernels or quantum components with being able to handle a lot of that today. So additionally, combining that with classical NLP pipelines that can also kind of bring out that hybrid sense. The biggest thing here is it's on the front. You're looking at the frontier of the aspects of quantum AI. So there's not really any true aspects to this that is bringing like real transition to the business and all that stuff. But it's on the realm of where we can start looking at potentially how can we make new AI models faster and better and grow stronger effectively using a lot of the new quantum algorithms that are coming out as well. Kind of next to that is quantum networks. Kind of briefly on this, the big thing here is this is another potential option for quantum computers because they are such, whether and I'll get into the part of talking about the various different types of quantum computers here in a bit. There's a number of different types. That being said, most of them are limited to a number of various qubits, just due to the aspects of quantum error correction, and a bunch of other things. So there's this realm of thought to allow for distributed computing aspects. And so where we connect multiple quantum computers together to effectively allow for a larger collection of qubits to process effectively. That being said, quantum networks are just as sensitive as their quantum computing systems, just due to the fact of most of the devices that do the reading are not very good. That being said, there are some other aspects in the realm of photonic systems that use typical fiber optics and a bunch of other things like that can allow us to do quantum communication over fiber optic systems. So there's a bunch of different pieces inside of there that can help us as it stands today. But this is just one thing I kind of wanted to put out there. One of the big things that are being researched is quantum key distribution. And honestly, I think the Chinese are kind of really holding tight on this aspect, and they have gone pretty far on their various pilots and research and test beds. We have a bunch of stuff here in the US, and there's some in the UK as well that they're building out. We're hoping to have a quantum network established inside of the next couple years. And then I know there is also effectively a kind of like quantum satellites and such. The only problem with them is that you have to have complete direct line of sight, and a lot of it is still very experimental, just because of the amount of, especially in satellite realms, you have the whole atmosphere that can potentially cause interference with inside of your quantum state and a bunch of other things. And so there's a bunch of realms that cause problems for this. And so it's possible. They have proven it with a very sense of research, but it is very early stages as it stands today. But yeah, so continuing on, we'll talk a little bit about the various different quantum hardwares. Just kind of jumping into the best part is that you don't have to build your own quantum computer in your basement today. Even if you wanted to, it'd be very difficult. But the cool part is that there's a lot of quantum cloud services that exist today, and SDKs, and quantum hardware that's accessible for researchers or developers, just to kind of allow you to grow and understand in this space. So firstly, the quantum hardware itself comes in several forms. The different companies and labs are building qubits out of different technologies, superconducting circuits used by like IBM, Google, Rigetti, and then there's trapped ion systems used by IonQ and Quantinuum, and then neural atoms, which is Pascal and QEra, and then photonics, which is used by Xandu and others. Each approach has pros and cons. Superconductors are currently fast and integrated, but can be often noisy, and they also require a lot more effort to kind of reduce that. Effectively, if you're familiar with having to reduce down to super cold temperatures to keep them not as noisy. And then there's trapped ion, which have very high fidelity, but their gate speeds are super slow, which kind of makes it kind of difficult. Great, we can sustain qubits, but we can't use them actually for logical gates, so it becomes difficult. As an end user, typically you don't have to worry about these. A lot of these systems have been figured out and put in place to allow for different usages, and they created high-level platforms on top of this to make our lives easy. With inside of that, this is just a couple other aspects that we'll talk about as well, but we'll touch on that here in just a minute. But for that, there's a couple different cloud tools that you can effectively go out and use today. Amazon Bracket, and Bracket is just kind of a throwback to quantum computing and some of the notation that's inside of there. But Amazon Bracket is a service that provides a single API interface with multiple quantum backends. You can work with IonQ's ionic trap system, Rigetti's superconducting qubit processor, or even other devices from the Oxford quantum circuits or QEra's neutral atom device. So it uses a standard called OpenQASM, or OpenQASM, and has a Python SDK. So effectively, you can write the program once and then try it out a bunch of different hardwares to make your life easy. And then Microsoft Azure Quantum, it's another hub. It's a cloud workspace where you can submit quantum jobs. It supports its own quantum programming language called Q#, and the Quantum Development Kit. Touched it once or twice. It's very interesting. And then you can also use it in Python. Most of their hardware connects to various types of partners like IonQ and then Quantinuum, and then Rigetti. And then you can also use it with a bunch of other workflows to optimize it and make it more for optimization solvers, and go through that same portal type aspect. And then there's IBM's quantum system. It has they've been kind of a pioneer on this, putting their first quantum computer on the cloud back in like 16. They have their own open source SDK called Qiskit, or it could be pronounced like 16 different other ways, but I think the most common one is Qiskit. So their systems range from a very small 5 qubit device up to their current largest one, which is our current I guess their current one is a 127 qubit processor, and they recently announced another 433 qubit system, which is on their roadmap currently. So a bunch of different things. You can use the SDK to run a bunch of different experiments in either in an interactive mode or even in queued batch job mode. So makes it easy for you to try to design and build your own hybrid kind of systems. Additionally, there's a bunch of other systems like IonQ Cloud. It's more on the hardware native tools. So like these are effectively the folks who have built the system have effectively started their own clouds. They start their own data centers and allow you to access their system directly through their public clouds that they host. Quantinuum has one. It's called Nexus, and they use a toolkit called Ticket. They have a Python library called PyTicket, and allows you to access their various systems. And they have a roadmap that's pretty aggressive, and is projected to have more qubits with inside of their system here soon. And then Rigetti's as well as has a quantum cloud service as well. And they have a language called PyQ, or it's a software stack called PyQuil, and the language is Quill. And then it allows just for quantum instruction language similar to assembly for quantum, effectively. That being said, we have a bunch of different SDKs. Well, I'll touch on Pascal real quick. Let me go back real quick. There's Pascal, and then QEra. These are just two other SDKs that are out there that allows you to use. Pascal is a French company, and then the QEra is the neutral atom platform. It allows you to kind of build your systems on that. So practically speaking, if you want to try out a quantum computer, you can do it right now via the cloud. Makes life a little bit easy. You can typically write a program in Python using one of the SDKs with just a few API credentials. You can run it on real quantum chips from your laptop. Makes it a lot easier to start testing this out and how to build kind of your hybrid comparison of doing various different types of implementation with your classical computing and your quantum computing right next to it. That being said, we'll jump into some of those SDKs as well. Here's just a collection of them. I won't probably go through them because I've already kind of touched on them. They all kind of attach to each individual group, so based off of their cloud. Some of them can go across different ones. I think Qiskit is probably the most diverse just because it was one of the first out the gate. Google came out with its own, but it plugs into the IonQ system. My personal favorite that I've used is actually Quantinuum's Ticket. I've used it a bunch. I used also Microsoft's Q# and Quantum Development Kit as well. Both great tools to use just to try it out. One that I have not honestly used much is the NVIDIA CUDA-Q. Not saying that it's bad or anything, but it's just something that I haven't gotten into yet. But they all have their realm of the world and they all work effectively. Penny Lane is kind of another one that I have not had much time to use. I see that it has a bunch of different interesting realms and the aspects of hybrid ML with quantum computing as well. So there's a bunch of different tools that are always coming out just because everybody wants to kind of be the first to like take the market in that sense. But personally, I like using PyTicket just because it's easy to use. You can just install it and start using it. So from there, we'll go into some simulators. These are some just other technologies that are easy to use and kind of help with tools for error mitigation, a bunch of other things for your quantum networks. TensorFlow Quantum, it's a kind of Keras-style hybrid quantum machine learning. It's heavily used with the CERT-based system or SDK. So that's kind of another big thing that's out there. And starting to use the IonQ kind of realm that is available to you through Google Cloud. Additionally, there is this language standard, the Open CASM 3. This is just a functionality or a standard that most of these languages should be following. Just allows for easier usage across different types of quantum computing systems. This space is highly collaborative right now, just because that it requires so much collaboration just to get any sort of movement forward with the research itself. One last thing I will call out here is AWS Quantum Ledger. This does not actually use quantum like computing behind the scenes. Why they use the aspects of what they call it quantum ledger is honestly just that they're saying that the system is hard built to protect against the encryption breaking algorithms that quantum computing represents. And so what AWS is promising here is that if you drop inside of the quantum ledger, that your database would be relatively protected in the sense that it won't be easily hacked in the sense of the new quantum computing encryption breaking aspects. So that's just the one thing that to call out there. It's kind of a misconception is you use that tool just as a note there. So jumping into it now, if you're an executive, you're probably thinking, this is all great, but what can I actually do with quantum computers? What are the use cases and matters in my business? And which was kind of a perfect segue. Let's talk about real world applications, the bleeding edge prototypes, the research in the various industries that effectively hint at how quantum computing might deliver value. So jump into that. The number of different applications and areas that we'll talk today is mostly around the aspects of finance, transportation, logistics, and supply chain, the energy, mostly around power grid manipulation and usage, and then pharmaceuticals. We'll discuss how kind of quantum computing is being applied in each of those areas and what benefits it promises. So in the finance realm, finance industry is heavily about numbers, risk, and optimization, fertile ground for quantum algorithms. Several areas in finance push classical computing to its limits, such as portfolio optimization, risk modeling, options, pricing simulations, and fraud detection. These happen to align with well-known or suspected quantum speed-up aspects. So why does quantum matter for finance? Because quantum computers can, in theory, evaluate many possibilities simultaneously, they could vastly accelerate tasks like exploring huge investment portfolio space for the optimal mix, or simulating thousands of market scenarios for risk analysis. Quantum prototypes promise faster, deeper search of portfolios and risk space, enabling things like sharper pricing, real-time risk management, early detection of anomalies, a bunch of different. So a concrete example, portfolio optimization, deciding how to allocate assets to maximize returns for a given risk. This is a complex optimization problem, especially when you have nonlinear constraints or many assets, a bunch of different things. Banks like JP Morgan Chase have run actual quantum prototype projects to evaluate portfolio optimization and credit risking using quantum algorithms. In one case, JP Morgan prototyped a quantum risk simulation, essentially a Monte Carlo simulation of credit defaults, to see if a quantum approach could cover more scenarios faster than classical methods. The results hinted that a quantum algorithm might scale better as the problem size grows, potentially allowing more granular risk analysis that goes beyond the classical methods that are currently feasible in the exact same time. While classical systems might simulate, say, millions of scenarios, the quantum version would feature larger qubit systems effectively examine billions by leveraging superposition. So the aspects of millions to billions is substantially better looking at it from an outside view, right? So fraud detection is another kind of intriguing application. Financial fraud like credit card fraud or trading anomalies often involves spotting subtle patterns in streams of data, essentially an anomaly detection or pattern recognition problem. Quantum machine learning might help here by being able to detect very subtle correlations or nonlinear patterns. For instance, a quantum combination, a quantum classifier might flag transactions that might see in when seen in a certain combination, indicate fraud, but that the combination is too complex for a classical rule-based system to catch. This being said, they have run a bunch of various different types of tests on this, and they actually found that utilizing quantum systems in combination, and then compared to classical systems, that quantum systems were able to detect 40% more fraud cases than classical systems in a shorter amount of time. The biggest problem is that it wasn't consistent enough to be able to do this, but it was consistent enough for the statistical probability to actually validate that it was proven to be an effective business case for it. That being said, it's just due to the lack of the system being sustainable for long periods of times and a bunch of other things that makes it kind of not an easy implementation as it stands today. So outside of that, there's a bunch of other business impacts that kind of come with this. The big ones are kind of in the realms of quicker discovery for exposures, tighter pricing on complex products, and a bunch of reduction in computational costs. So as soon as the systems start to come in play, you can kind of offset some of the more heavy computation calculations that you're doing on classical systems and put them on quantum systems to make your life a little bit easier. So that being said, we'll jump over into the aspects of logistics and kind of supply chain. You can think of the challenges like optimizing delivery routes and managing traffic flows in a city, scheduling fleets of vehicles, or routing airplanes, routing trains, you name it. These are classical combinatorial optimization problems, often just NP hard problems. These are things that occur as it stands today and are very difficult to solve, both with traditional classical computing or machine learning or AI, all that stuff. It's very just difficult to solve. And this is where you can use this combination of quantum computing with classical computing to effectively do a lot of this stuff. And so one of the traditional approaches for the combination of classical to quantum is that your data processing, your pre and post processing of decisions are effectively handled by classical computing, and then your quantum computing does the really hard, like calculations and combinatorial optimization aspects. And so from there, you can kind of look at as quantum computing offers kind of a new approach to solving this. There's also another kind of realm into this that we're going to touch on is called quantum annealing. It's a quantum-inspired optimization solution, effectively. There's companies called D-Wave that provide quantum annealers that are designed to help solve optimization problems by finding low energy states of the system, essentially solving something formulated as a minima inside of a complicated function. If you're familiar with how AI and machine learning and the computational effective process of a stochastic gradient descent, it's just trying to find the minima of effectively of a function to allow you to make a proper prediction on that system. So with while quantum annealers are a bit different from a gate model, quantum computers are where, like we mostly discussed, they leverage quantum effects like tunneling to potentially escape local optima in an optimization landscape. And what that means is that there is theorems inside of quantum mechanics that if it runs into some sort of hill, that it can pass through that hill if it's not its actual minima. And so effectively, it doesn't fall into the same trap that traditional machine learning and classical computing runs in today with the aspects of that you're system can effectively try to build a model and it'll fall into a local minima and not the true minima. And then that results into bad predictions. And so with quantum computing, you can actually pass through that and deal with, you get a better result of a prediction model with that. So that we'll look at looking at like real-time traffic routing. Imagine a city's traffic control system that tries to continuously optimize signal timings or suggest routes to alleviate congestion. This problem can explode in complexity because every driver's route choice can affect others, which results in a very, very, very complex situation and optimization problem. Classical methods like greedy algorithms or even advanced heuristics often get stuck in suboptimal solutions. You can adjust some routes and you can alleviate one jam, but causes another, etc. Quantum annealing could help here by escaping those local optima, essentially trying more global route adjustments that a classical heuristic might not be able to consider. In quantum annealing, all possible configurations within some formulation are explored in parallel in a fuzzy way that thanks to the quantum annealing aspects. The systems can sometimes jump through energy barriers, local traps, to reach a better solution than classical gradient descent like approaches that might get stuck. So back to exactly what I was saying. This is just kind of one of those realms of areas. And I think there was, I can't remember the car manufacturer. There's a car manufacturer out of Europe that actually did this and has this, they're exploring this realm of being able to do this within certain cities to help with this and actually integrate it into the cars to help with better traffic routing and handling all the various different things. So end of the day, it still comes down to individuals' decisions on whether they choose to go certain ways, but they've started to look at the operational impact and see if they could get better real-time rerouting and during like accidents or heavy congestion, reducing overall gridlock and improving travel times. Outside of that, we'll jump onto the energy side of things. Energy sector is kind of a huge space for this, especially with inside of dealing with different types of energy networks and various different types of plants. It's the same realm of things. It's another NP hard problem. Power grid optimization is one of those big things, right? So the huge combinatorial optimization problem that the grid operators effectively solve almost every day or try to using classical optimization solvers is it's not to the realm of which we could solve it comparative if we used quantum computing. With all the new introductions of like things like solar and wind, it kind of adds another realm of uncertainty and planning that becomes difficult because solar and wind can kind of fluctuate on how much power it introduces into a grid. There's a bunch of different combinatorial aspects that we have to take in consideration with our other more stable realms of energy providing sources too. So effectively, researchers have started delving into this concept and started developing a quantum-assisted optimization algorithm for grid scheduling. One approach is actually using hybrid quantum classical loops. And it works effectively in a sense where the classical system sets up the problem. For example, a linear programming can help relax this solution or a partial assignment of which plants likely need to run. Then a quantum solver, like an annealer, or gate-based variational algorithm, is used to explore the combinatorial space of on-off decisions for plants and other discrete choices in the schedule or other solutions that are out there. The quantum part can churn on trying many combinations. Let's say like turn off these 10 plants or turn off this or turn on this one, which then exponentially, which is a huge space for it to effectively store. Then it finds a candidate solution that is near optimal. And then a classical post-processing comes back in to verify those candidates, solutions against all constraints, power, flow, equations, a bunch of other things, and then pick and adjust the best one. Essentially, quantum helps in the search of the part of the optimization, while classical computing handles the actual fine feasibility checks and any continuous adjustments, like how much power each plant produces, and which can be continuous or variable, and a bunch of other things. So early studies are on the small scale, but have shown actual promise when it comes to producing real results out of this. One research that actually came out of this was from the Oak Ridge National Lab and IBM and D-Wave. They were able to work with understanding these aspects and produce actually good solutions in a less computational time than a classical solver. And then Los Alamos National Lab is also starting to go down this path and looking into this. So it's a bunch of different potential areas of research that are trying to effectively solve this problem. And so outside of that, there's a couple different ways that you can kind of jump into this as well as yourself. You can look onto that and start looking at a pilot and understanding those roadmaps and trying to work in that space as well. So additionally, we'll look into the realm of pharmaceuticals. I think this is probably one of the more interesting spaces just because it produces potential for new kind of drug discovery is kind of one of the big things. Chemistry and molecular chemistry and a bunch of other things is very hard to simulate. And so this is where quantum computing's natural ability to simulate quantum systems can effectively be revolutionary for them. These processes are governed by quantum mechanics, electrons and atoms, and a bunch of other things that's just due to the aspects of chemistry and what that is. The equations of quantum mechanics for many electron systems are too complex to solve exactly. So we rely on approximations that become inaccurate for large complex molecules. This means drug discovery often involves a lot of trial and error in the lab and because our simulations can only guide us so far. And so that's where quantum computing kind of comes in and helps us deal with that aspect. And so there was a breakthrough example of this. Qubit Pharmaceuticals is a biotech startup, and they used that French company called Pascal. It was a quantum computing company. They provided a hybrid quantum classical simulation to predict how water molecules arrange inside a protein's binding pocket. Now, why is that important? In drug design, when a drug molecule binds to a protein, like fitting a key into a lock per se, there are often water molecules in the pockets that can influence binding. And some need to be displaced, and some may need to be mitigated in other cases. So predicting where these tiny water molecules sit in is crucial for accurately estimating how well the drug will bind or effectively be effective. So this Qubit and Pascal team used a neural atom quantum processor to effectively understand this and effectively prove out a way to computationally calculate this more effectively with the quantum system. So just allowing for faster development of drugs based off of various different factors that they had to go through and effectively learn and understand about this. With inside of there are a couple different things I want to jump into as well. So, I mean, we talked about the four industries of finance and a bunch of areas in the sense of finance and then chemistry and pharmaceuticals and a bunch of other things. But the biggest thing is there's a different challenges that are kind of coming up in the sense that we're kind of preventing us from having realistic expectations, or not necessarily realistic expectations, but the challenges prevent us from actually having solutions that we can use today. So mostly just trying to set realistic expectations as to what is currently happening with these systems and how can we kind of look forward to handling them or grow with them. So the one big thing here is the hardware limitations. Qubit count and the quality is kind of the biggest thing here. For superconducting systems, it's very difficult because they require very cold simulations environments, and so that's very difficult to maintain. It's very cost ineffective, well, comparative to classical computing. And so there's that limitation of where we need to have large scale number of qubits at room temperature. That's something that's kind of difficult. But that's where some trapped ion systems come into play. They just need to figure out how to optimize the logical gate calculation problem with that side of things. And so there's all these different various systems that all have their various different types of constraints. And so that's one of the big things that we have to look at and understand. Outside of that, I think once we get past the aspects of technical challenges that are coming up, the next half of it is honestly more on the organizational side. It's very similar to what happened with AI in a sense. During, I'd say, probably early 2000s to the mid 90s, only few people were actually doing AI, actually putting implementations of machine learning in place and a bunch of other things. And it didn't take until probably the aspects of large language models where people saw the actual value of it. And so the big challenge organizationally wise is that what we saw in AI is that we did not have enough people to actually operate and do these functional tasks and gain expertise and understanding to operate in this sense. Quantum computing is going to be the same thing, but at a different level because it requires a different level of thinking and understanding about the quantum aspects. And then on top of that, quantum computing just operates a little bit differently comparative to traditional computing. I believe that most of the research and engineers who are putting systems in play is kind of trying to avoid that barrier and putting these systems in a sense where it feels very similar to traditional computing and that we can use programs to develop these systems effectively. That being said, there will be a talent shortage in quantum computing, and just in the sense of being able to use these various different types of SDKs and being able to solve problems with it. So once the systems are in place, where do you have engineers that actually come in and are able to build systems with this stuff? And so that's where the kind of talent shortage comes into play. And then eventually it'll correct itself. But it's better to be on the forefront of it than kind of falling up behind. That being said, quantum computing is not for everybody. It is only meant for very specific hard problems. And you have to really understand the aspects of your business and the problems that you're trying to solve and whether or not your problem actually falls into the MP hard category aspects. And that's honestly where a lot of this will kind of come into play. So outside of that, that's the integrated quantum into your workflows is kind of another part of that. But the nice part is with all the SDKs that are coming to play, that's kind of coming down and making it easier to do. That being said, a lot of people say that there's a lot of hype around quantum computing. I don't necessarily think that's true. I think AI kind of takes most of that right now. But the biggest thing right now is it's still in an R&D phase. It's not meant for full production. It's meant for seeing what is potentially possible and building those solutions and figuring out as to once a true solution comes to play, how are you going to handle that going into the future? So that being said, looking into the future, there's a bit of a roadmap that I'm starting in that sense to kind of help folks as to, okay, what does that mean as a leader or as an engineer? How do we start to look at getting ready for this aspect of quantum computing? So mostly I've started to build a strategic roadmap to start looking at that. It's based off of this kind of lessons learned from the AI aspects and what that looks like and moving into this realm. So as we have new technology that comes into play and grows, this is where this kind of comes into play for us. So the big thing here, because I noticed that I'm probably short on time here soon, the biggest thing, I'll run through the high level topics. Establish executive sponsorship and vision. This is a key thing that happens with any kind of major strategic decision that needs to happen. Invest in talent and education. This is another big thing. Have them start to learn, understand quantum skills. You don't necessarily need somebody who has a PhD in quantum computing or anything, but start looking at your different ways to upskill your team utilizing the various different types of codes. There's also the Quantum Economic Development Consortium. They provide a bunch of different national hubs to help industry partners start to look at different types of talent and then also early access to tech and how to bring that into your organization. Think of hybrid and complementary solutions, things that you can do classical computing and quantum computing together. And then start small. Find pilot projects. It's very similar to how the AI realm, AI era started, is that you start with small projects and find ways to gain some sort of value out of it or potential value out of it. And then that way you get hands-on experience, you grow your individuals and their ability to understand it. Additionally, collaborate and join an ecosystem. Don't go it out alone. That's one of the big things I would say that is kind of key. This is just a very collaborative space right now. Try to keep your own PII and PHI, if you have it, separate and figure out problems that you can solve that doesn't kind of introduce that kind of complexity. And then just kind of monitor and process. Oh, wow. Monitor progress and of your competitors and a bunch of other stuff as well. And then understand the research, where it's going. Have kind of a small team that helps you understand as to where is this ebbing and flowing and going towards, or listening to our talks, because we'll probably have more talks on this. And then manage risk. Make sure that you're understanding the aspects of where is what's called post-quantum cryptography at, and what does that look like, and then timeline and milestone planning, and just have even just the high-level aspects in place will help you look at it from the next year to 2 years to 3 years to 5 years, which is something that we actually look at here, is understanding the aspects of the era of prototypes, the early quantum advantage, and quantum in mainstream. So the early era of prototypes, that's honestly where we're at. This is potential on like how research is going to grow and expand. This will probably spread into me, honestly, and I'm probably an optimist. I think the era of prototypes will extend at least into the next 5 years, unfortunately, and the early quantum advantage won't actually start until 2030. And then maturity and mainstream adoption will probably be 2035. That's how I personally see it, but some probably would say that I'm a pessimist in that sense, and others would probably say I'm an optimist. So it just really depends on who you talk to, I think. But it just based off of what I've seen and the adoption of it and what it's actually able to do, and looking at the research, this is kind of where I foresee things going. That being said, it doesn't hurt to start on early era prototypes and like get an understanding and start doing some hybrid systems. That way, once the time comes and you actually are able to solve your really hard problems, you can just jump into it and go from there. And then communicate and evangelize internally as well. Try to build internal teams and make sure that you're able to move forward together. So that being said, in conclusion, there's a bunch of stuff we talked about today. Quantum computing, quantum AI, quantum networking. How does all this stuff work together? A bunch of different use cases, all in all, the kind of future roadmap of where this is going and how you can grow to bring this in. So I apologize for probably going over just a little bit here, but thank you for bearing with me, and happy to take any questions.